Hello, everyone. We're excited to present our senior design project, Wind Power on the Go. I'm Alban, and I've worked along this project beside Justin, Alenton, and Puneet under the guidance of Professor Kevin Shanley at SUNY New Paltz.
Problem statement. People in sub-Saharan Africa village of Kamituga require auxiliary power source for their new solar-powered lighting system due to the fluctuations in available sunlight year-round.
Design was a critical part of our solution since we're harnessing wind energy. Selecting the right blade configuration was critical. We evaluated HOT and VOT systems, which stand for horizontal or vertical axis turbines, where horizontal is generally more efficient but require alignment, while vertical axis types can operate in much more variable wind directions. We also focused on achieving a high lift to drag ratio to boost startup speeds and maximize our power output, especially important for portable small scale turbines like ours.
Combat Kamituga's robust environmental requirements, our design had to be modular, transportable, cheap, and very easy to maintain. There are a few user requirements that we had to meet in our engineering of this wind turbine: portability, lightweight, reliable energy output, durability, stability, and we want it to be environmentally friendly, but material limits require us to use plastic.
Mechanically, our design was grounded in aerodynamic and gear design principles. We used the tip-to-speed ratio equation to guide our blade RPM relative to wind speed and optimize lift and drag coefficients to enhance energy capture. We also used the minimum gear tooth equation to ensure smooth and reliable gear meshing while minimizing mechanical losses.
The most important electrical equation we used is the power equation. For the DC to DC buck converter basics, the formula for that was V out equals to D times V in. D is a duty cycle between 0 and 1. The For the MPPT algorithm, we used perturb and observe. Perturb means slightly change. So we measure and store the input and the input voltage and input current, and then measure the output voltage and output current, and then compare with each other and see if the change is greater than a zero, meaning we're getting more power, then the algorithm keeps pushing the slight change in that direction. If not, then we reverse the direction so we can get a maximum power at all times.
Two key iterations helped improve the design. First, we optimized our gear ratio starting from 1 to 1, which didn't generate enough torque. We shifted to a higher gear ratio of 4 to 1 to better match our generator's needs. Second, we added a spring mass dampener system, 3D printed to isolate vibrations. This reduced mechanical stress and made the system more stable during operation. Both adjustments helped us move from concept to a functioning, testable product. Speaking of which, did it work? Yes and no. Our experimental results matched our theoretical trend with an R-squared value of 0.9, meaning we saw the expected relationship between wind speed and RPM. But the actual RPM values were only 17% of what we predicted theoretically. This highlighted real-world losses, like friction, generator drag, and less than ideal airflow. Still, we proved the concept and gained key insight into how a system like this behaves in practice.
Technical components, damping system, combats vibration experienced during shaft rotations. DC to DC buck converter steps down the power so the battery can be charged safely. Arduino takes the readings from the voltage and current sensors and gives it and uh, and puts it into the algorithm to give us the maximum power. The generator converts the rotational energy from the turbine and converts it to the AC electricity.
And for some takeaways and considerations, we found turbine generators operate at a far higher speed than anticipated. So we had overestimated exactly how fast our turbine would go. We also assumed that the size of our turbine blades would be big enough to generate that required lift. However, the simulation we tested for our model didn't account for the frictional effects caused by other components. Thank you.
Thank you.
Thanks for watching.
Yep.